Okay, I think we'll get started with the lecture today. I'm trying to use my phone. We'll see if that helps out a little bit. Maybe I can upload it quicker. This is for Physics 302. We're going to talk about electric potential today. We talked about the curl of E last time. So introduce a little bit of potential, make some comments about it, and I'll get up to Poisson's equation and Laplace's equation. I want to do that in class. Well, I was going to try to be in class on Monday. If my test gets back in time, I will, but who knows? I had to get another test Friday. It's a story. So let's talk about potential a little bit. Let's talk about potential. So this is section 2.3, electric potential, and 2.3.1, I'll just call it an introduction. An introduction to potential. They basically say that the electric field effectively is a special type of vector. It's not just the average vector. The electric field, it's a special type of vector such that the curl is zero. The curl of the electric field is zero. And that means it doesn't rotate. It doesn't want to have a circulation about it. So electric fields don't circulate around about themselves and cause drains and you go down to the bottom of the sea and stuff like that. They don't tend to do that. This is for an electrostatic field where you have moving charges. You might do it. This is a static charges. So because of that, they're going to look at this and try to make it to a scalar problem. If you think that del cross E is zero, that means then that the line integral of E around any closed loop is zero as well. Now, where did that come from? Well, remember we talked about what del cross, a del vector, the curl is? If we go back to fundamental theorem of divergence, fundamental theorem of, not divergence, fundamental theorem of curls. There you go. So if del cross E is zero, and that part right there is zero, then the other part is zero. That's the cow part, because it's the other one. So that part right there has got to be zero. So if that equals zero, the other side has to equal zero. And so if the other side equals zero, let's look at this. So what they're going to say is the line integral, so from 2 points A to B, and so we'll make A here and B there. And they just go, if you go wee, and get here, and go there. So it doesn't matter how you get there. Line integral between any 2 points is the same. So that the line, if I go from A to B, it doesn't matter how I get there. As long as I just go from A to B, that integral will be the same. It doesn't matter path. Path is independent. Okay? Path is completely independent. If I integrate along this path, if I go over here, go underneath there, and go around, I'll still end up, when I do my integral, with the same answer. Okay? Because it doesn't want to circulate. The curl is zero. All right? So what they say is, let's take this electric field and integrate it over this path, over some dl, and they put an O here, and I don't like that. Basically, we're just going to call it some standard reference point. And when we get to electric potentials, I'll kind of explain how that's going to be what we normally think of as zero, but that's further down the line. Okay? And what we're going to do is we're going to say this by definition, and actually I'll keep that there. Make the negative of it. You got to take the negative of it, because it's going to be from some standard reference point to R, and we're going to say that equals something called V. And this V, which only depends on R, and basically R is, where you are between the 2 points. Okay? We're going to call that the electric potential. That's supposed to be an A. So if we do this one, so the electric potential, now that's potential. Lots of times that's what we care, what is the potential difference. We're going to care about what is it here versus there. Think of it as, you can think of this as elevation to some extent if you want. What's the elevation change from, Hickory to Boone? Well, that's so many, 1,000 feet or a couple thousand feet or something like that. Okay? So say this would be the the electric potential, I haven't called it voltage yet, at B minus the potential at A. And that would just be the integral at some reference point to B, negative integral E dot dl, plus integral from 0 to A, E dot dl. And we have a visitor. We have a visitor. I must acknowledge my visitor. We have a visitor today. Hello, Miss Chloe. Chloe. Come on, Chloe. This is Chloe. She's the cat. She must not be camera shy. Chloe, what's the matter, girl? Oh. You good girl. You don't want to be held right now, do you? All right. There you go. She's my barn cat. And she wasn't here other day when I filmed, but she's here today. All right, so let's go back. Chloe didn't like the wind and the stuff on the metal roof and stuff. She don't like that. All right, so if we do that, what we notice is, I put a plus there. Okay, so it was minus this one. Why is there a plus there? Because it was minus a negative. Because this minus that makes that a plus. Well, what if I flip that? I can flip that and make this equal to negative 0 to B E dot dl minus A to 0. Because when you flip them, you go put the negative out front. E dot dl. Well, why would I do that? Well, if it's going from 0 to B and A goes from 0 to B and then A to 0, I can just do this now. I can combine these two and say that's really just minus my integral from A to B of E dot dl. Now, this gives me the potential difference between 2 points. I got limbs falling from the old hickory nut tree on the barn. So this is E dot dl. So this is potential between these 2 points, A and B. They basically use the fundamental theorem of gradients. I'm not going to do that. I'll just say use the fundamental theorem of gradients. And you use the fundamental theorem of gradients, basically this integral equals an integral with a del operator in it. So this, basically, you can show that the electric field is equal to minus del V. And that, my friends, is big idea. So as long as you take the gradient of the potential, you can get the electric field. That's interesting because all this stuff before, we were finding electric field really from first principles. I can measure voltage. Voltage I can measure real easy. Electric field, a little bit difficult, more difficult. I can measure voltage real well with a voltmeter. That's why we call it voltmeter. Voltage is like, you can think of it as electric potential. So as long as I know the distribution of V over a space or over an area, or from a line, in this case, over a line, I can find the electric field there between those 2 points. That's a lot easier. So in reality, you can find electric field from first principles, which is what we've done. Or if you can measure the voltage, you can back out the electric field that way. All right. I like how it say, notice the subtle but crucial role played by path independence. The mathematics, the key here to make all this work, to make that work, is path independence. It doesn't matter how you get there. Okay? It doesn't matter how you get there. So, and if you think on elevation, it's the same way. If start at Hickory and walk all the way up to Boone, I have changed from about, 1,000, 1,100 feet in altitude above sea level to, say, 3,000 feet above sea level. So I may have went up 1,900 feet. That's my change in altitude, which I would call my change in potential. So this would be, of course, I could write this as delta V. Okay? Write that as delta V. Now, does it matter if I walk down to the beach, went all the way up the coast to New York City? New York City. I will go in New York City, walk over to the Appalachian Mountains, come down the Appalachian Trail, and then stop off in Boone and stop right there. What was my original and starting endpoint? Difference in altitude. It's still 1,900 feet. Doesn't matter how I get to Boone, if I go straight up 321, or if I take a very roundabout path to get there. The altitude change is still the same. The change in potential between 2 points in an electric field is still the same. Doesn't matter what path you take to get there. You still have the same potential. Okay? Now, that's section 2.3.1. I'm going to turn it off, and we're going to look at comments on potential.